I'm Calvin, and I'm from Indiana University, and this work was done with Doctors Kuehlkamp and Nabrzyski at the Center for Research Computing at Notre Dame. Um, and we're talking about characterizing the transfer graphs of suspicious ERC-20 tokens on the Ethereum blockchain. Just to provide a brief background, obviously, Ethereum blockchain launched in 2015, similar to something like Bitcoin. And its notable innovation was that it let users program smart contracts in specifically Turing-complete bytecode. So it sort of solved the problem of users writing non-terminating programs and how you can deal with that and still let them write, these powerful applications. And it's led to the creation of cryptocurrency exchanges and decentralized organizations and a whole range of uses of this smart contract functionality. What we're interested in here is the use of smart contracts to implement so-called tokens. So, the representations of value of membership in an organization. And in order to standardize interactions with these tokens, the Ethereum community adopted the ERC-20 standard, which describes an interface for an implementation of fungible tokens. So that makes it easier for, users and applications to interact with these tokens. Where here fungible just means that there's no difference between any two tokens, much like if we're talking about like if I have two different dollar bills, there's no significant difference between them. And notably, the ERC-20 standard requires this transfer event to be emitted to the blockchain whenever tokens are exchanged between users. And this will be used to construct the graphs of tokens that we see in a bit. So yeah, it's possible to represent the blockchain from the perspective of a graph. We see here an example. This is not using real data, but just sort of see what the structure of a graph could look like, where each of the nodes is a different user address or contract address potentially on the blockchain. And we have arrows between them whenever one sends a transaction to the other. And there can be multiple transactions between nodes. Nodes don't have to interact with every other node in the network. So this is a useful perspective for seeing what patterns and structures emerge from the interactions of people on the blockchain. There's been work done looking at sort of how the blockchain compares to social network structure, trying to correlate the changes in network structure to external events and other modeling of the cryptocurrency network. And since the ecosystem is so diverse, it can often be useful to only consider particular subgraphs of sort of all of the transaction behavior that's happening. So maybe only looking at when users create a smart contract, or only looking at when users actually transfer ETH or like Ether currency between each other. Or what we're doing here, which is only looking at transfers of ERC-20 tokens. And what we want to do is we want to use these transfer networks to detect malicious behavior in Ethereum. Since there's so much value in the blockchain ecosystem, that means there's also lots of people seeking to exploit that. There's been a proliferation of counterfeit tokens, and a variety of other scam behaviors, Ponzi schemes and rug pulls where token values are brought really high and then sold out before people can get their money back. So it is very much still a problem, and research is being done to try and combat that, and has found some success, particularly in detecting malicious user accounts. So studies have looked at, this is a small selection, but transaction behavior and graph topology, and even analyzing the bytecode of a contract to try and see if a contract might be implementing a Ponzi scheme. So there's lots of work done. But for the most part, the research has focused on malicious user accounts rather than malicious tokens. And the work that's focused on malicious tokens is more so concerned with trace of the tokens on decentralized exchanges, or things where it's very evident that it's a counterfeit token. What we're interested in finding out here is whether if we take these fraudulent tokens and look at their network structure, are there significant differences between these and legitimate tokens? And can we use those to build some sort of model to predict whether a token is legitimate or not based solely on some of the traits of its network? In terms of our data set, we scraped all transfers between blocks 18 million and 20 million, which is roughly August to June, using the git logs endpoint of the JSON RPC API that Ethereum requires nodes to implement. And we took all of the logs and then filtered out, taking only the ones that have an event that matches the event signature for transfer. This left us with a huge number, 269,000 total tokens that were exchanged in millions of different transfer events. And we limited our analysis to the 8,000 tokens or so that had more than 500 transfers in a given 100,000 block, time span. And the reason for that was just in looking at the distribution. It's a really long tail distribution as networks get bigger and bigger and bigger. And we wanted to limit the search to a manageable number. And if we went really any further beyond 500, the number of contracts that you would have to consider ballooned really quickly. And of those 8,000, we ultimately marked 3,600 suspicious. And the way we did that was just looking at the site's Etherscan, which is the largest block explorer for Ethereum and has a community-based scam detection mechanism where users can report malicious behavior. And then the site honeypot.is, which looks more so at token scams and whether looking at their traits on the centralized exchanges like Uniswap, whether the token is something worthwhile investing or whether it carries too much of a scam risk to really be worth a user trying to invest in. So we considered if either of these services marked a token as a scam, we would mark it as being suspicious in our data set. So like I said, we looked at each token in 100,000 block timeframes over the course of all 2 million blocks. And we constructed a graph for every token in every 100,000 block timeframe that it occurred in. You see here, this is the transfer event structure that I was talking about a little bit earlier. Here, it's got this from trait, which is sort of the source vertex, and the to trait, which is the destination vertex of the edges in the graph. And we're really only concerned with the transfers of a particular token at a given time. So we aren't looking at here whether a user is trading maybe USDC and also that's like one particular token or another particular token. And whether like, oh, is this user using a lot of scam tokens? That's not something we're looking at here. But that would certainly be a direction future research could go. So in terms of the features we want to choose features that let us capture information about how the network is structured and be able to connect those features to malicious behavior. There's a lot you can do. I mentioned, approaches taking topological analysis, using sort of more complex mathematical methods, graph stats like diameter and centrality and clustering are all sort of different things we looked into and ultimately decided not to use in favor of simpler measures because those were sufficient to show the link in the structure. I'll mention lifetime because lifetime, though not necessarily purely information about the graph, was successful in a number of cases in detecting scam behavior. And we'll see that bears out here as sort of the malicious accounts are going to pop up and they'll work for a little bit, but then they're going to go away as they move on to new targets and they're discovered and things like that. So here you can sort of see the distributions of the 8 features we considered with the suspicious contracts in red. I'd just like to draw attention to a few of these. First of all, like I said, lifetime, we see borne out. Yeah, you know that the legitimate contracts are all going to be going the entire 100,000 blocks. And the scams are shorter, very few last more than 20,000 blocks. We also see some interesting things in terms of the number of components and the size of the components. So almost, or like the vast majority of scams are either going to be one single component, or have a lot of these, a spike down at having maybe like 2 to 3 components, or components of an average of 2 to 3. So a lot of different components in the network, but each of them is only like 2 or 3 accounts. And we'll see in a second as I pull up some of the networks that we looked at. These correspond to sort of 2 different types of scam behavior. So here are sort of some of the networks of the tokens that we considered. These top 2 were legitimate in our data set. BAT is a token associated with the Brave browser. If anyone's familiar, it's the token that browser uses. And USDC is a common stable coin that tracks to the value of the US dollar. And both of these, though BAT is much smaller, have this similar pattern of a really big sort of connected central component and a sort of smaller external behavior from that. So there is like activity centralized maybe around a bunch of like decentralized exchanges that it's trading in or applications that it's used in. But then outside of that, the token's still being sent from user to user, and like other things are happening with it, which heuristically is something you would expect from a legitimate token. The 2 on the bottom are 2 different scams, and they correspond also to the spikes we saw of scams of one component on the left and scams of lots of really small components on the right. We found that the scams with one big sort of star-shaped component, like Shia coin, were some sort of like rug pull or honeypot-based scam where the scam is really happening around a decentralized exchange. The scam is getting users to invest in that token and then somehow taking away the value they invested. So, a rug pull, we get the value really high, everyone invests, we sell, we get that invested money essentially, and the people who invested can't really pull back out. The other is a counterfeit token for USDC above it. And this is something that's been referred to as an address poisoning scam, or perhaps it is like connected with a phishing scam where like, oh, you got sent a bunch of money, like pay us to get it back or something, right? And this is where a scammer will send to a user a token that looks very similar to one that they usually trade, like USDC, from an address very similar to one they normally interact with. And the hope is that the user will just glance at the beginning of the address hash or something and accidentally send money that they meant to send to like a different account to the scammer. And that sort of bears out the patterns we see here in the distribution of features. And now turn to sort of the training of our model. We just opted for logistic regression for its simplicity. We're working with only 8 features, and this makes it really quick to train and test. There's lots of different options to choose from in the literature that do perform better than sort of logistic regression models on equivalent data sets. But again, like here, we're mainly focused on a simplicity of approach and sort of a proof of concept that there is merit in this connection. So what you're seeing over to the right is we evaluated each span of 100,000 blocks. We trained the model on all of the networks in that span, and then evaluated it with 5-fold cross-validation. So, training on one portion, testing on the rest, and then doing that for all sort of different partitions to try to eliminate any like problems with overfitting. And this approach achieved 88% accuracy, which is comparable to what other logistic regression models were achieving, and over over all of the block periods. You do see that the recall metric and with it F1 score really drops off towards the end. And the principal reason for this is that there's fewer false positive samples in, fewer positive samples in these later blocks. So, recall dropping off is going to mean that there's a lot more false negatives, which means that the model is probably failing to catch on to some of the patterns that are important for detecting the suspicious behavior. It's also possible that the community-based efforts we used were not, comprehensive, and that there are remaining scams that we don't have labeled in our data set. And that's also causing issues with performance, especially, more recently there's less time for the thing to have been reported. So that's something to keep in mind. We also see, though, that these network characteristics are able to be used predictively. So what this shows is a model that was trained only on the first 100,000 blocks and then was tested using the rest of the time spans. And we see it still maintains like average accuracy of 88% or so. But now we see additionally a drop off in F1 score, as well as the sort of other statistics that track similarly to how they did above. And again, this is because there's fewer suspicious contracts in these later blocks, at least according to our data set. So the model's expecting to find more than actually exist, and that leads to this sort of reduction in performance in those other metrics, while accuracy is able to stay relatively high. So to conclude, we've shown that there are patterns in the transfer network structure of malicious tokens, and we don't really need complex models to capture this. With our really simple features, a really simple model, we were able to find this connection and make predictions about suspicious tokens. And that these patterns are consistent across multiple time periods. So week to week, scam behavior, at least as far as it's borne out in network structure, is going to be staying fairly consistent, which bodes well for the use of this technique to improve scam detection tools. Like I was saying, our limitations, or one of our main limitations, stems from having an imperfect ground truth, and with improved classification of this training data set, we likely will see improved performance, whether that's an additional human component of labeling, or drawing from more data sources than the two we used. That's certainly something that could improve the model. And additionally, looking at cross-chain behavior of tokens and using time-based techniques for analysis of these networks might also yield fruitful future research. But this is a great first step at showing that there is a connection between transfer network structure and suspicious behavior that can hopefully improve on community-based detection efforts and improve the safety of the blockchain ecosystem. And with that, that's everything I have. I want to thank you all for your time.